I see Zoom's changed their annoying pop-up about meeting being recorded. Let's start. Another minute, a little less than a minute or so.
When do you arrive here?
November.
November. Are you a postdoc at Berkeley right now?
Yes, I'm a postdoc in Berkeley, but from this network, so I'm in San Diego.
Right.
Yeah.
Yes. Meaning you're physically in San Diego. Yeah. Is that in the astrophysics department or in the physics?
It was in the astrophysics and physics department, but there is a split happening
Yes.
now. So I think because I work with George Fuller, I will move to physics.
I see.
Because
Okay.
he was also director of the Center of the Space Sciences, but now that's dissolved. So
I see.
think he's gonna.
So one department is becoming two.
Yes, I believe it was a physics and astronomy department and is now
Oh,
two
wow.
departments.
Where's Raphael Flauder and Dan Green going?
I think physics.
That answers a long-standing question we've had about Flogger.
Yeah.
Is he a physicist?
Whether he's a physicist or an astrophysicist.
There you go, there you go.
Subject of many arguments.
Back in the day, was he also No, he was half IS.
Yeah, I don't think so. I think he was physics. Anyway, that was the origin of those arguments, yes.
Sorry. It's, yeah, I know it's, yeah, so if you just go to tinyurl.com/ccpp events, and then you'll go to it, yeah. Okay, awesome. All right. Should you want to make sure you can, yeah, so go, okay, great. All right, we should go ahead and get started. So we're very happy to have Anna Suliga here today. So as we were just saying, Anna is a postdoc at San Diego and Berkeley, but she's going to be joining us next November as a postdoc here. So we're going to hear today about some work Anna's been working on neutrinos from supernova collapse. So please take it away.
Okay, so thank you very much for this invitation and for wanting to hear about my work. So I will be mostly talking about the neutrinos coming from cold-cloud supernovae, either from like single events or something about the diffuse supernova in the background. It will be a description of few papers, so if you have any questions during this, let me know. I think it's hard to talk about the cold-cloud supernovae without mentioning 1987A, because that was the supernovae that we detected not only the electromagnetic radiation but also neutrinos. So if we think about that event and look at the emission of different messengers, I believe this was a first non-solar observation of multi-messenger astronomy. So we have luminosities in neutrinos in those more red lines up, and we have some gravitational radiation, and all of that stuff is arriving quite early because those are things that happen inside the core and then just kind of free-stream away. And then if we talk about the chromatic radiation, it needs to go through the whole envelope, so that is later. So one thing we can think of is that these neutrinos and potential gravitational wave can be a ways to point to the supernovae, which is really cool. And here are the data points for the 1987A, so that supernova was around 50 kiloparsec away, so we don't see that many events because it was pretty far, and also the detectors at the time were not that big, but it still proved that those collapses of very massive star emit a lot of neutrinos. And right now, there's been some debates whether or not actually this data can be explained with the current supernova models. Some people say that it cannot be, even in the early evolution. Some people say that early evolution is fine, but then the cooling of the proton-neutron star is a bit hard because of these late events at seconds of thinking can account that. So there's not yet consensus, and that kind of means that we want to have core collapse supernova simulation that run not only for until the explosion starts, like it was happening in 3D, but we also want to know what is happening in this later evolution to see the other part. And of course, right now, if we would have the supernova, Super K can discriminate pretty well, at least beyond some classes of those 3D simulations. You can see that.
Super K is the successor to Kamiokande,
Yes.
which
okay,
is still running.
It's still running.
Yeah.
It's still running, and it should run.
Okay.
Yes.
But people are arguing about like whether the thing on the right fits the data on the left, the predictions on the left.
The predictions from the current simulation. So people said that most models don't really match, given the early times, like here. These people say that it matches if you have low mass proton-neutron star inside, like around 1.4.
I see.
And this is just like future predictions, but this is a very nice paper, so just to add it.
Okay.
Okay, so when we look at this more cartoon picture, then we know that the core collapse supernovae are for very massive stars. So when we have these balls of gas that go through different phases of fuel burning, in the end this will form conical shell-like structure. And for stars with masses approximately above 8 to 10 solar masses, once this inner core will grow to substantial size, meaning that the degeneracy pressure of the electrons can no longer support the gravitational pull, the core starts to collapse. A lot of electrons is captured on the nuclei or some free protons, and this produces a lot of neutrino emission. And at some point, the density is so large that neutrinos become trapped and our collapse proceeds adiabatically to the point of saturation density, when our infalling matter basically hits the brick wall, bounces back, we have a shock wave, potentially very easily exploding the star because we see the supernova explosion. So in this case, it's important for me at least because we have a lot of neutrinos, and again, they are emitted from very deep inside the core of the star, so they carry information from this deep core. And in addition, they might be the only messengers if we have kind of collapse direct to a black hole, maybe some gravitational radiation if we are lucky, or potentially some electromagnetic thing if we are also lucky and it's really bright. But in the zero approximation, they could only tell us about those dark collapses. So why these?
Sorry, is that like that's a generic prediction that neutrinos will come out if it's a direct collapse?
If it's a direct collapse of a black hole?
Yeah.
I mean, so they are already emitted once the star starts contracting.
Okay.
So either you form a neutron star or black hole, and usually you form black hole once the shock stalls and you cannot revive it. At least this is from the simulation. So up until that point, you will see emission of neutrinos in both cases, and then if it's from a neutron star later on, you will also see the cooling of the helpful neutron star.
Okay, so there is like some sort of constraint on the number of those from not seeing them. Because people talk sometimes about these direct, like collapsing without a supernova happening.
Yeah, so if it's close enough,
I didn't
we will
realize
see
this
that.
was a constraint, that we hadn't seen any
Yes,
others in the LMC, right? For
yes,
example.
yes, that's a constraint on the number of the close by supernova,
Yeah.
I would say. Minus anything that all of the detectors at once were turned off.
Right,
But
yeah. I mean, it's a weak constraint, I think, but.
yeah. So like the core collapse rate in like cross proximity can be constrained, or the core collapse to a black hole that can be constrained potentially.
But do you still emit the, like 10 to the 58 neutrinos in that case? I mean, because don't you need that large of a flux to even detect them? So can you put bounds on them if they emit a lot of neutrinos?
So I will show luminosities later, and I will show you when like the cutoff to black hole formation will happen. So it will be at least half of that you would still see, because of most of the neutrinos is emitted in the neutronization phase and accretion phase. But yeah, you would still see neutrinos if they are close enough.
Right. And on the previous slide, you said with gravitational waves and neutrinos, you both have information about the collapse. are they totally overlap, or the gravitational waves like only do the very, very last stages and the neutrinos just like kind of the early stages, or do they actually have most of the same information?
Yeah, so I think you can potentially see some neutrinos even before the bounce, and for gravitational waves, I think mostly with the bounce case when you have some asymmetry, which I think you would nature for sure see. I don't think that there is, I'm not an expert in gravitational waves, but I don't think there is yet consensus on what exactly would the template for this type of event look like.
Cool.
If anyone is expert, just tell me wrong. I'll be happy. Okay, but I'm excited because it's a pretty extreme laboratory. First of all, it's very high density, degeneracy, temperature, but also those neutrinos travel very long distance, the longest distance that we ever detected neutrinos in 1978. So with the future detectors, which we have this data running right now, June of, they say they should be operational end of the year, maybe next year. And also some of the large-scale dark matter detectors and future detectors like Dune, Berkeley, we will see not only single flavor as we saw with those detectors and so on, those are electron antineutrinos, but multi-flavor detection. And it can give us also even 10,000 of events depending on how far we can see the supernovae. So we will have more precise information about maybe about the explosion mechanism, how it's happening. Maybe this can be connected with the heavy elements formation, compact object formation, again, black hole, neutron star, maybe some potential non-hadronic thing. And also it can give us more of the particle physics unknowns, like what is happening exactly with neutrinos in these very dense environments when they can interact with each other, which is very highly nonlinear process. But also if there is any connection with non-standard phases between neutrinos and of course all the particles. And there's been a lot of work done in the field, and people run simulation 1D, 2D, now there are many 3D simulations. But it is a very complicated process involving many fields of physics, so it's still being in the development phase, I would say. So here we can see, for example, the spread of the mean energies, I think all mean energies for different neutrino flavors with different progenitor masses that were run. And here, which I think is very nice, we can see the difference for two progenitors from the same group, for this Oak Ridge group, that differ in the second decimal point. And we can see that in this case, the luminosities and mean energy changes quite dramatically with such a small difference in the mass, which can kind of indicate that maybe this is not entirely stochastic process, what is happening in the supernovae. So this would be kind of important to see not only one event, but of course one event would be great, but more events. So that would be the second part of my talk, with more events. But first, I wanted to talk about something that would be exciting for maybe close progenitor, otherwise it would be pretty hard to see. And this was work done with two great at the time graduate students and Baha, but now Tanya is also a PhD postdoc. So we try to look at the quark-hadron phase transition in the accretion phase of the spark plug supernovae to see if by using this signal of neutrinos from this quark-hadron phase transition, we can put limits on the masses or the location of the supernovae. So I think we know that normally if we look at this diagram, temperature, density, and the degeneracy, we live somewhere here very nicely. We have atoms, so only electrons are inside atoms. But
sorry, what's the dimension this way?
this is the degeneracy, this is like number of neutrons minus number of protons, the asymmetry.
Okay.
Yes. But in this very extreme environment, we can have conditions that the matter is no longer in hadrons, but maybe we can have some quark matter. And people have asked questions where we can look for that in some of the astrophysical environments and how we could see that. So some of the places that people have looked at are the, for example, old neutron stars that are accreting matter, becoming dense and can turn into quark matter. In the proto-neutron star after the collapse, when there's still some fallback on the star, But also, especially for our case in the protocompact star, during the early close-down phase, so not yet when the star explodes. And this is the part we looked at.
Can I ask, what is quark matter? Like, what does that mean? I don't know what quark matter is exactly.
So in the case that we looked at, it would be a mixture of U and D quarks, just living freely, connected by some strings, and then this part, they I don't know, I'm not sure.
So it's like, but I should think of it as like the neutron star is something where things are still in neutrons, but this is a state where there's no neutrons, there's no protons, it's just the quarks
So,
and whatever they're interacting with.
yeah, whatever they enter in the most dense part, yes, that will be the case. There will be some regions in the density and temperature that we still have normal matter, at least that's what I would think, of neutron protons, and then in the core, potentially, if the conditions are good, there could be quarks.
And then but then we don't actually know like its equation of state, so we don't know what pressure it provides or what.
Yes, so I
Okay.
think there are many models. This model that we talked about is assuming that we have quarks that they found in hadrons, and when they become more and more squished together in those hadrons, they'll be connected by some strings, and once you can become very close together, they can kind of more favorable position is when they connect with the neighbor from the other. So it's kind of like a soup thing. And if I assume that I only have N and P in terms of protons, that would be only U and D state. At least the simulation that I looked at. I didn't run the simulation, I didn't construct the equation of state. So this is
Okay.
zero order my knowledge explanation. Which
Okay.
can be
So
wrong.
it's an increment above mine, so go ahead.
Yes. So we're gonna go here and just quickly, if we zoom in what is happening in this core cloud supernovae in the very inner core, we have our info of the core, and once this inner part, which is saturation density, the shock wave is formed. So this is the nuclear saturation density and can travel through the core, but we see in the simulations that it stalls after traveling around 100, 200 kilometers. But we know that supernovae explode, so there needs to be something that injects the energy back to this shock wave that is stalled. And this zero order hypothesis that mostly works now in the 3D simulations is that the neutrinos, which are still produced by this very central compact hot object, will travel a little and inject enough energy back to this shock that it will feed on the hydrodynamical instabilities and explode the star. There are some issues with that. First, the very mass stars, so like above 30, 25, 0H main sequence mass, this doesn't work always. Another is that this cannot produce hypernovae, so very high explosion energies. So people try to look for different solutions to that problems. One would be if we have magnetorotational instability, so when there's a lot of there's rotation in the star and the magnetic types are twisted, this produces pressure which would help our shock wave explode. Another thing would be if we allow some physicality on the standard model, there are several solutions. I like the stellar neutrino solutions, so we can look at 100 MeVs stellar neutrinos, which then decay to pions, pions potentially to photons, again, energy injection back. Or if we look at the keV neutrino mass range, we can have MSW, like in our sun, increased production of the steroids, even when we have very small mixing angles. And for electron neutrinos, the conditions are such that you produce a steroid, it travels a little bit as a stellar neutrino, but then can reconvert back to the active neutrino. So that would again inject high energy neutrinos produced.
Sorry, I'm having a lot of trouble understanding
Sorry.
some of your words. Just maybe if you should help talk louder, that would help. But what do they convert to?
The
Oh,
active
stellar
neutrinos
neutrinos.
convert to stellar neutrino and then back to active.
And that helps because
That helps because the steroid was produced deep inside the core when my temperature and neutrinos were to bound to the matter, so they had like temperature around 50 MeV. And I didn't go through the lower density and decouple them to 10 MeV, but they still have 50 MeV description of their distribution. So then I basically injected this very high energy neutrino back to the region where normally the active neutrinos has lower energies. So that can then help to the shockwave again.
So being sterile, it just goes through the rest of the stuff
Yes.
without, okay.
But the last thing is if there is this phase transition to the quark matter, I can again think of this scenario, but now my inner core can potentially contract even more and produce first mixed phase between hadronic matter and then quarks. And finally, if it converts into pure quark matter, in that case, this equation of state that is describing this pure quark matter is more stiff. So I have the same mechanism as I was approaching nuclear saturation density. My inflowing matter will hit again the brick wall, and I will produce a shockwave. But also, you can think of it as if I'm just boiling water up to the point that everything is above the 0 temperature. It doesn't really boil, but then once it starts boiling, I have.
Could you just try talking louder?
Oh,
I'm
sorry.
really sorry, I'm
Yeah.
really hard of hearing, I guess.
Yes, but basically the idea is that I have a second shockwave that is produced by the quark-hadron phase transition, which then joins our first stalled shockwave, and that can drive the explosion. But in that case, if we look, here is the neutrino signal, so I have luminosity and mean energies of neutrinos emitted from the star. This is the neutrinosation burst, and the accretion phase here is pretty prolonged, but usually it's up to a second. So this would be how many neutrinos you emit if you would form a black hole, for example, here or here. So it's more or around half. That was the question. Yes. But here, if we have this phase transition that produces second shockwave, in addition to the neutrinosation burst, we also have the second burst of neutrinos. But now, contrary to here, when I had mostly protons, which then electrons were captured on, and I produced a lot of electron neutrinos, here the matter is mostly neutron rich, and also it's much hotter and denser. So first of all, this peak is mostly in electron antineutrinos, and in addition, the shockwave travels faster and through smaller region, so this width of the peak is much more narrower, which can help with looking at the neutrino mass and also localization of the star. And we try to look at this signal in the free future and existing, one of the existing neutrino detectors, which would be the Hamburg-Hamilton, so bigger super K, the ice Cherenkov detector, and also the Dune, the liquid argon detector.
So I have a question. Could you go back to the slide, one more slide before that? You were saying about this stereo neutrino after a couple oscillation turn into the active electron neutrino, which is have the two bursts, right? What was the time scale of that inside the neutron star explosion?
Yeah, so that was one of the potential scenarios that could produce the explosion of the supernovae.
Will that phenomenon affect this burst and this waves?
If there are these stellar neutrinos that would affect this burst, and that depends on the mass of the stellar neutrino. If we would look at the keV and higher masses of the stellar neutrinos, they usually neutrinosphere, so the point when neutrinos decouple from the star, the active neutrinos decouple from the star, is closer to us than the point when I effectively convert my stellar neutrinos, my active neutrinos to sterile. So in principle, that would mean that I don't see any peak features or dips in my spectrum.
So it's trivial for this burst you were showing.
A little bit, but if you add those neutrinos inside the core of the star and you allow them to escape or even transfer energy or shuffle, you take away energy from the core and you move it later on. So potentially this would make the phase transition not happen because you would have lower temperature in the core. So I wouldn't say that it is true that the peak would still be there if I would have stellar neutrinos of that kind.
Thank you.
Okay. But the main point is that it's a very sharp feature in neutrino signal that we want to use to look at the absolute neutrino mass and localization of the star in 3 big detectors. So here we show the event rate for these 3 different types of detectors, and we did it in 2 different oscillation scenarios, either full favor swap or non-oscillation, to kind of see the variability of.
You know what, I apologize again, you probably explained it, but what energies are you talking about right now? These are just MEV?
MEV neutrinos.
But weren't those the energies that were being observed by 1987A? It's the same energy
Yes,
scale.
it's the same energy.
And so the structure should have been there, was it just not visible?
Yes, so that was 50 kiloparsec away, and also the detectors were much smaller, so we wouldn't see something that sharp.
So it's not that it would have, that's what I was wondering, it's not that it gets spread out or something like that.
Yeah.
They should have seen it if they had simply had enough.
Yeah, if they had enough statistics.
Because in your picture, the peaks stick way up.
Yes,
relative-
but this is like this one is around 2 milliseconds.
Yeah, so like I think you said it, but like what fraction of the neutrinos are in the peak? Like
Yeah.
half of them or something, or less?
No, in this peak, there's like, for sure, maybe 5%. In this peak is like 25 to 50 milliseconds, so it's an order of magnitude longer.
And it's just computation that it doesn't go out? Because all the neutrinos that right, they came over, I don't remember the exact number, like
10-ish seconds.
18 or so
Yeah.
seconds.
Yes.
So that's on your plot really way later or not? And how would we map this onto the one we know from 1987A?
So I think, let's see if I have. So for the hyper K, let's say it's 10 to the 3 for 10 kiloparsec. So for 50 kiloparsec, that would be 1/25 reduction, if I'm not mistaken. So that would be an order of magnitude. And in addition, hyper K is I think here it's 200 kiloton, and then Kamiokande, I think, was 2 kilotons or 2 tons.
I'll tell you what I'm confused about, is the picture makes it look like at later times, there's way less integrated. So even if you didn't see a peak, it seems like you should have still seen events in the 1 second. There should have been many more events at 1 second than at 10 seconds. According, if I'm understanding, I may not be understanding right.
And I mean, I think the events kinda were clustered at early times. In most of the detectors, there are some detectors that see later events.
I see, fair enough. So you think those ones, right, people often talk about the late ones because
Yeah.
that is so informative.
Yeah.
But you're saying actually there are plenty at early
Yes,
time to
yes,
identify with that.
yes,
Okay, thanks.
Yes. So like, I don't know, like I was saying earlier that the early evolution, people kind of now say that it matches the predictions for the low mass proton neutron stars around 1.4-ish. Some people say that it doesn't match, especially for the larger proton neutron star progenitors. but the later times, both of them agree that it's kind of hard to explain. So in principle, like those events might have been the fluctuation of this very narrow peak, but I wouldn't see this very, very peaky structure because 10 kiloparsec compared to 50 kiloparsec, so that's one suppression, and then 2 orders of magnitude suppression from the fact that the detectors were much smaller. So I wouldn't see something that narrow. But maybe with the future detectors we could see something that narrow. Yes. So if we can see that and kind of independently of what is happening with the observations in both cases, in all of those detectors, we can see the peak. If we think about the dune, which would be the smallest one, I think the 5 sigma detectability of the peak is around 20 kiloparsec, so that's larger than at least the galactic center. And if we can see that, we can use it to time our neutrino signal. And we did that with just using the linear function peak because this peak is so narrow. So if we time it and then we look with different detectors at the arrival time of our signal, we can then with each pairs of our detectors constrain like a cone on the sky, which uncertainty is the uncertainty of the timing. And with 3 pairs of the detectors, then we can constrain the localization of the star to 2 points. Here our injected signal was at the galactic center. And this localization is much better than if we use neutronization burst, because neutronization burst is electron neutrinos, and we mostly have very good, at least right now, anti-neutrino detectors. And here, this was anti-neutrino signal mostly, but also it is much narrower, so that help us to determine timing much better. And it's not that far from the elastic scattering of electrons. It's 2 degrees, but depending on the detector, and also in the bad, good, depending how we look at that situation, when supernova is too close and saturates your detector, you cannot really use then electron scattering, but you can still use triangulation. So you don't have to ask for a smaller detector, but you can just use this thing. And in addition, you can use this very sharp feature to put some limit on the absolute mass of neutrinos. So if we think of neutrinos, we usually think before that they were masses, but we know that they have masses. So if they have masses, different neutrino energies will arrive at slightly different times. So if we look at the time shift, depending on what is the mass of my neutrino, we can then see that our peak would go down and broaden, and especially you would see that high energy neutrinos, high energy in energy scale still would arrive earlier than the low energy ones. So that puts the limit on the absolute neutrino mass, which is also better to the neutronization burst. On the level of the current limit from the Catherine, in the future this will be better or could be a cross-check. And of course this is more local so that the cosmological probes. So that would be this for a single galactic or nearby supernova, and now I will move on to cases when we would want to see more of the supernovae. So I was talking about something exotic that we don't know if it's happening, even if there is a phase transition. It not necessarily is a first order phase transition that will create such a sharp peak, but if this could help us. But in the other stars, we can have different type of collapses. And in principle, we want to see as many as those events as possible to discover anything that is hidden there. And in order to do that, we need to go to larger distances and accumulate more events. But the price to pay for that is, of course, much lower fluxes. And basically, the diffuse supernova in the background, this is what it is. It's a diffuse and isotropic background of neutrinos coming from all the past collapses. So here you can see the equation how they calculated and some ingredients that it depends on. So first would be the rate of the supernovae in our universe. Second would be, of course, what is the average neutrino flux coming from supernovae, and here I also distinguish different types of supernovae, neutron star versus black hole forming, because those will emit slightly different fluxes. We can, of course, go into more detail and add more and more structure to that, but in principle, fractional black hole forming and cosmological supernovae will be the two biggest uncertainties. So, still,
In that equation, what ends up being, where does the, where is there like some particular range of redshift which dominates?
Yeah.
You'll tell us,
Yes.
you'll tell us, okay.
Yes. So a lot of talking and no detection so far. Here are the limits from super K without the gadolinium. The ones that super K has no gadolinium, which is supposed to help it with detecting the SNB, are of the same order, but they needed 5 times less exposure. So maybe this plot with limits will turn into detection soon, but so far there are only limits. And the UV bar limits are again the best because that's the channel that we can coincidentally detect both products of the interaction of our antineutrino, so we are more sure and we can distinguish background better.
The curves are predictions, or there's some other limit?
Yes, so those are theoretical predictions, and all the colorful points are the limits from different experiments.
Atmosphere is to the right.
I think that, yeah, from there they will start. I will have a plot later that will show them. Yes, so UV bar best limits because this is the easiest detection channel. Electron neutrinos, there is limit from snow, maybe detectable in June in the future. Mu X, very hard. So other papers. So if we come back to the what is affecting this DSMB, one thing was the fraction of black hole forming progenitors versus fraction of neutron star forming progenitors. Because if I have a black hole forming progenitor, in principle, I can grow bigger and hotter core, which will emit more high energy MeV neutrinos, and that will be helpful for detection. But this parameter is unknown. It is unknown if it depends on redshift, in principle, if it depends on metallicity. There are some simulations and also observations, which puts the fractional black holes between, I think, 9 to 40%. There were surveys from Ohio group that looked at the disappearance of red supergiants, and now on one of the candidates there was a follow-up by JWST where they didn't exclude that star disappeared. And I think there is one more which is not public. I heard about it, but I haven't seen it on archive, so I don't know. So one thing would be to look for red giants disappearing. Other, maybe use the SNP to constrain that fraction. So as I said before, if we look at just one panel, I have my DSMB flux in antineutrinos, function of neutrino energy, and I focus on the single color and just go from the least solid to most solid line. I am decreasing fraction of black hole forming progenitors, so I am decreasing fraction of high energy neutrinos from this plot, which makes it hard to detect, but also changes the shape of my spectrum. So that is one uncertainty. The other would be the cosmological supernova rate. So here I have a plot of, I think, most redshift that would affect the DSMB. Most of things that would change a lot would be between 0 and 2 that come into the DSMB calculation because of redshifting of the energy and then the neutrinos falling behind the solar or reactor or spallation backgrounds. But if we look at these uncertainties, it looks pretty large. People see that this is mostly, even though the shapes are different, it will mostly affect the normalization of the DSMB as it was in front of our integral for the masses and the masses. So if we look at this plot, it looks pretty bad, but people look at the studies that with the Berkeley Observatory and the LSTC survey, and we will see a lot of supernovae per night, they can constrain this parameter much better, especially for 0 to 1 redshift. So at least part of it has a lot of impact on the DSMB. As I said, this is the biggest. So that can help us. And then detection of DSMB can be treated as with better uncertainty estimation of the cosmological supernova rate as a way to look for fractional black hole progenitors. So we did that study where we looked at the detection of DSMB in 3 future generation detectors, HPK, Juno, and Dune. So here we can see fractional black hole progenitors for different oscillation scenarios of neutrinos. But mostly what we can see here is that having a dune, which is detecting electron neutrinos versus anti-neutrinos, as the other two do, kind of breaks the degeneracy a little more than just having additional inverse reality detector.
Sorry, can you, what is this? I'm not sure what this plot is showing.
Yeah, so this is the 1 sigma uncertainty on the fraction of black hole progenitors if my true value is somewhere between those parameters. In case of normal oscillation scenario in my star, when I just have MSW for my neutrinos, and this is for inverted ordering.
Okay.
So this is the same now, but 1 sigma uncertainty for the normalization of my supernova rate. And again, having another channel detection, which is the neutrinos, is helping even more than having more anti-neutrino detectors. So yeah, I think for this one, we assume at least 30% 1 sigma uncertainty when marginalizing over for the supernova rate. But if we know supernova rate better, this uncertainty can go down. And there's many more smaller things that will affect the DSMB. Maybe this one is kind of interesting. That I think right now people think that most of the stars are in binaries. I think also now for 1987A, people think that this there is a factorial ring around the star, so that it means that there was a merger event in the past. So if we have binary interactions between stars, in principle, we can change the DSMB, because to the first order, we can, of course, reshuffle number of progenitors that undergo core collapse. So this can increase potentially DSMB. Okay, so with that many uncertainties, is there anything about looking for beyond the standard model physics with this flux, or that doesn't make any sense because I already have large astrophysical uncertainties? And together with Bakhan, George, and Anupam, we thought that potentially maybe, and we can look at the potentially dark matter steroid candidates, which are self-interacting. So in this scenario, I have my light mass eigenstate coming from DSMB, which is mostly pink, so that means active neutrino, with a little of sterile. And I have my produced some way in the early nucleus, agnostically how, population of heavy neutrinos, which is mostly sterile. And I allow for those sterile neutrino interaction by some secret dark mediator. So what will happen is that I will downscatter my DSMB neutrino, and I will upscatter a little my heavy dark matter neutrino. If there is a right combination of the mass of the steroid and my mediator, and also my detector resolution is not that great, I can approximate the this interaction with just delta function. So I would eat up some neutrino from my flux, and that would show up in the DSMB as a dip. And what is important in this dip is because with so much astrophysical uncertainties, which are mostly shifting the spectrum or changing the normalization, dip is something that can be constrained even if I have large uncertainties.
Sorry, can I just understand the notation? M phi is
That's my mediator, sorry. That's the mass of the mediator. This is the mass of my spheroid. That's the resonance energy, which I want to be in the 14, 15-ish MeV to say 30 MeV range of neutrino energy to see that in the detector.
right. Yeah, so M sterile, people always talk about KV
Yes.
for reasons.
Yes.
But M phi
So for
is
this
just some,
I think it was 0.1 MeV to make it right. Yeah, that's a.
that would put it in the right range
That will
for
put
you
it in
to
the
see
right
it.
range, yes.
I see, but there's no natural choice of M phi.
Maybe there is. I'm
Okay.
not a model
Okay.
builder, but
Yeah.
I will leave it to the smartest people. I just want to see if there is anything
I
that
see.
I can
Okay.
see in the DSMB and that would make sense to look for.
Yep.
So this is star neutrino with self-interaction. Yeah, because star neutrino, potential dark matter candidates, potential signatures that people don't really believe, but some still believe. And yet the mediator is there to create a dip in my DSMB. So if I look how I can modify my DSMB flux, to first approximation, I would say that I don't produce star neutrinos in core perhaps supernovae with key mass range, which is bad, and you should never do that. But we do that anyway because this is conservative. And it's conservative because here I'm summing only for active flavor of the light mass eigenstates. The heavy mass eigenstate would have small contribution of the active flavor. So that would be just addition. But the thing that can change and make the bound more stringent if I would allow for the possibility of creation of heavy mass eigenstates in my supernovae would be this factor. So the suppression of my flux would don't have the steric contribution because I would be taking M4, which is mostly sterile. So adding the sterile production in the supernovae could only make my bound better. So for that reason, we allow ourselves a little relaxation. And here we can see how the event rate for the DSMB as a function of my positron energy, so I'm looking at inverse beta decay again, looks like. Here are the atmospheric background, and here is some of the stellation background, and my standard DSMB without any self-interacting star neutrinos, and then what is happening for those parameters of the sterile mass and mixing and mediator mass. So I can see that part of my spectrum is eaten up, but the rest looks smooth. And that is very different if my slope would change or the normalization of my DSMB would change. So we did the Harris-Burr test to make the limits on the mixing angle of the sterile neutrino with the active and the mass of the sterile neutrino, assuming that I would see my dips between the energy range that is in the DSMB detection window, and then marginalize it over different shapes of the spectrum. So we change the temperature of the neutrinos emitted from the supernovae and also some normalization. So basically, to the first order change what the proper supernova rate looks like. And we got those pink limits, which are overlapping with the future sensitivity of the Tristan detector, which could be a successor to the Catherine, which is looking at the absolute active neutrino mass, but this could be looking at the TeV sterile neutrino masses. So if we see the DSNP and there is a signal in Tristan, that would suggest that there is a self-interacting stellar neutrino. And potentially it could also say that there might be not only stellar neutrino and this one dark mediator, but some other particles, because in this range there are some constraints from, for example, Lyman and alpha forest that say that there cannot be that massive, but I think it's mostly if it's warm dark matter. So if there is a way to make my neutrino cold, this can still make 100% of the dark matter, my stellar neutrino, my self-interacting stellar neutrino. So if you have a good model, you can look for that. I have one more part, but I don't know if I have time.
You got about 10 minutes.
Okay, so all I was talking about for the detection of DSNB mostly was for electron antineutrinos, but then maybe electron neutrinos if we look at Dune, because those are easy to detect. But what if we want to detect the heavy electron flavor neutrinos? So we looked if that can happen with the large-scale dark matter detectors or 7s detectors for neutrinos with John and Irene. So again, if we look at our DSNB as a function of energy, here is the fluence, and we add what are the truly irreducible fluxes. This would be the atmospheric neutrinos and also the solar neutrinos. But even if we look at this DSNB, which is the sum of all favors, there's still a window where we can potentially detect it. But we want to detect mu nu and mu tau for that have energies around, I don't know, 20 positively, I don't know, optimistically MeV energy. So that means it's only neutral current detection, which is very hard for those low fluxes because I only have one particle that can tell me this interaction, and there is a lot of bypass. So the current limits are around tens of times worse than what are the predictions, theoretical predictions. And they come from the neutrino scattering on electrons in super K. But we try to see if we can do this again with the 7s. So coherent elastic neutrino nucleus scattering, when a neutrino is coherently scattering of the whole nucleus, if it has right energy. This channel is to the first order favor insensitive. And in addition, the cross section, if we look at this spot, is much larger for large nuclei because it's basically increased with IBD around number of neutrons in my nucleus. This is almost 0. So that's the gray channel we could look for potentially. Other thing is that for this thing to work, we need to detect the recoils of the nucleus around key UV energies, which seems hard, at least for neutrino detectors. But right now, for the dark matter detectors, this is possible. And there exist large-scale dark matter detectors, and in the future there are planned even bigger. They can detect those low thresholds for really good efficiencies and pretty large volumes. So let's do this. And we tried to look first at xenon. So here we can see the event rate in recoil energy of the nucleus. We see the DSNB and then solar atmospheric. But now atmospheric are over the DSNB. And this is because if we look at the differential cross-section for 7s, even though high energy neutrinos can produce high energy recoils, still the most probable ones are low energy ones. So this atmospheric spectrum smeared over to the lower energies. Well, it looks bad, like for the detection, but maybe we can at least improve the limits on the DSNB with this. So here we can see again the event rate, now with some detector efficiencies and energy resolutions. Our standard DSNB prediction, and the one that is 1,000 times bigger, so at the level of the current limits from super K. So we can see that this is 1 to optimistically 2 orders of magnitude better, which means that these detectors could put better limits. And here we can see blue on the left-hand side limits if we just allow the S&D normalization to change. So this is the prediction level, and the blue line is the limit that we get with increasing the exposure. So we can look at the benchmark xenon collaboration type detectors. So it's still not detection, but potentially already Darwin can make only 10 times worse limits than what actually the S&P is. And this was done for the fixed temperature window, but once you start seeing some atmospheric neutrinos, then you can make little adjustments to make these limits a little better. And we can also ask the question, what if we not only allow for the change of normalization of the S&P, but also the spectral shape? So this is the mean energy of neutrinos emitted from supernovae, and this is the total energy of neutrinos emitted from a single supernovae. So we can again see the limits with increasing exposures, the 100-ton years. So few to 10 of years running Darwin is at the level of the nu E limits for the S&P already. So not quite there yet, maybe. Oops, no. But if there will be very large detectors, maybe there. So I think that's it. Okay, sorry. Yes, thank you very much for your attention and letting me know.
Any questions? I had one. On the sterile active neutrino interaction where you have that phi mediator, you said like its mass needed to be fairly light so that you could have the resonant conversion or the resonant scattering, right?
Yes, but this is only coupling to steroids.
Right. Like, do you have issues though cosmologically with producing it because it was so light? I mean, because you had dark matter was your sterols, right?
Dark matter is my steroid, yes.
Right. I mean, did you look at cosmological bounds on the light phi, or does it? I mean, it decays to sterols and actives, I guess, or does that give you unaffected because its mass is like MeV scale? You said, right? Or is it lighter than MeV?
It's lighter than like this one is 0.2 eV, it's below MEV. So I think it wouldn't. At least I'm not sure how if it only couples to steri, and then if I have some mechanism that allows them to decay to my steri neutrino, and then that will produce the right number of dark matter, I'm not sure why that would be a problem. I don't have a model how to create that. It's just more of the experimental perspective. Like, if this is impossible, then that's bad, but maybe there is a way to produce that relation.
And that phi doesn't have a vev, right? Because it's just a plain scalar without any.
Yeah.
Okay.
For the diffuse type of thing, is it helpful at all? I guess it's not really that helpful. It's that like the optical wide field surveys are not that helpful because they don't time them interestingly. Like it's not like you can stack up a bunch of supernovae because you don't know when they've happened accurately enough. Sorry, I'm thinking out loud. That was probably not very clear. I had a different question, which was, can you when are this new generation of supernovae, of neutrino detectors happening? Hyper Kamiokande is 2027.
2027, I would take it with a grain of salt, and I think Dune date might be also a little pushed back. In addition, this prediction was for 40 kiloton. I think they are approved for like 10 now.
These numbers are comparable to each other? Is it a ton of argon the same as a ton of ice? Or whatever this is a ton of for Dune?
I think they are mostly comparable. I mean, you can see that Dune has lower number of
Right,
rings than
yeah.
Berkeley because
And Ice Cube, there wasn't a date on Ice Cube.
Ice Cube is already.
It's already going, but
Yes.
they're, okay, oh, so,
This is with the existing Ice Cube.
But
right.
it doesn't have the high resolution center, does it?
Yeah, so for Ice Cube, we cannot see the energy of the neutrino, but they can still see the increase in their background. Like it still will produce flash of light because of a lot of Cherenkov happening at the time of the supernovae. So this is the event rate that is energy integrated. So that's how it would look like in the Ice Cube. They have heat spooling. I think that was the case, which they tried to estimate the sensitivities to the supernovae, to low energy supernovae neutrinos. And I think they said that the timing resolution, I thought that might be a limiting value for this narrow peak because the default that I found was like 1.7 millisecond, the time resolution. But they told me that it can be lower and you assume 0.1 and like they said that this is realistic.
This generation, if an 87A went off, how far away could they see it, like, in an interesting way? Like, does it get you out to any interesting distance? I guess not, really.
I mean,
Well, I mean, like, an interesting distance would be like 10 megaparsecs.
I think maybe 1 if I remember correctly. But that would be optimistic for the.
Okay,
I
so
can
really
I
just,
should check that, but yeah.
really still local group,
Yeah.
yeah. Okay.
What about this KM3AET? Does it help with the supernova neutrino detection?
I think in principle, yes. I don't know what's the timing resolution
It's such a
with
small detector, right?
KM3net.
Yeah. Is it?
I thought it's like in water, that's pretty big. Maybe not as big as Ice Cube. I don't know exactly. And I don't know, I don't know about the detectors, I'm not sure. But I think they have some sort of sensors. I need to look into that. So.
Any last questions for Anna?
You'll
No?
be here all week, so.
Yeah,
if
so
you
you'll have
have
time
any
to ask.
questions, let me
You're
know.
912, right?
Yes.
Right, okay. Alright, well, thank you.
The idea of doing